Hi everyone, we are Group 5 and our project is on face recognition. We will be walking you through our approach, our results, and what we found along the way. So let's get right into it.
So face recognition is a biometric system that identifies individuals by extracting and comparing their facial features. It is widely used in security, authentication, and surveillance because it is contactless and scalable. However, face recognition is challenging. Variations in lighting, pose, expression, and accessories significantly changes the pixel values. This highlights the semantic gap. Pixel level similarity does not necessarily correspond to identity similarity. Two images of the same person can look very different, while two different individuals may share similar low-level patterns. Therefore, success depends heavily on how facial features are represented. While modern deep learning models achieve remarkable performance, they typically require large-scale datasets. In contrast, the AT&T ORL dataset contains only 400 images across 40 individuals and just 10 images per identity. This creates a small sample learning problem. Under such constraints, training deep models from scratch is impractical. This leads to a critical question. When data is scarce, how important is the choice of facial representation? So our research question is, can classical PCA-based Eigenfaces achieve performance comparable to pre-trained CNN embeddings in small-scale face recognition? We compared two fundamentally different representations: linear subspace projection using PCA-based Eigenfaces and non-linear hierarchical embeddings from pre-trained ResNet 18. Both are evaluated using the same linear SVM classifier. By keeping the classifier fixed, we isolate the impact of representation quality. So face recognition has evolved through three major stages. Early methods such as Eigenfaces uses global PCA projections. These were simple and interpretable, but sensitive to illumination changes. Later, approaches introduced handcraft local descriptors like HOG and LBPH, improving the robustness but still relying on manual design. Since 2012, deep learning has dominated, with models like DeepFace and FaceNet achieving near human accuracy using learned hierarchical features. However, these systems typically assume abundant data and computational resources. This makes it meaningful to revisit the classical approaches under small data conditions. So we evaluate both methods on the AT&T ORL dataset with only 400 grayscale images from 40 subjects with 10 images per identity at 92 and 112 resolution. We used an identity stratified split, 7 images for training and 3 for testing per subject, resulting in 280 training and 120 test samples. Experiments are repeated across 5 random seeds, and results are reported as mean and standard deviation. Both pipelines uses identical linear SVM classifiers and five-fold grid search CV tuning. The only difference is the feature extractor. Therefore, any performance gap reflects the representational power of each approach.
So let's talk about why we chose transfer learning over PCA. PCA is a traditional method. It looks at all the pixels in the image and tries to find the most important patterns. But the problem is, it has no idea what a person looks like. It's just finding general patterns in the data, not learning to tell people apart. Transfer learning is completely different. The model we used was already trained on millions of face images. So it already understands things like facial structures, like eyes, nose shape, all the things that makes one person look different from another. That's a huge advantage before we even start. And this becomes even more important when you look at our dataset size. When you have a small dataset and you use PCA, the model doesn't have enough information, so it ends up picking up random noise instead of real patterns, and it performs poorly. If you try to train a deep neural network from scratch, same problem, not enough data. It would just memorize the training images and fail on new ones. But because we're using a pre-trained model, all that face knowledge is already built in. We only need to train the final step, which is the classifier. So even with limited data, we get strong, reliable results. So that's the main reason we went with this approach.
Let's move on to the two experimental setup. Pipeline A follows 5 steps, and you can see them here. It starts with a raw image, 112 by 92 pixels, all in grayscale, then gets flattened into a single row of over 10,000 features. Then it goes to a principal component analysis, PCA. It looks at all 280 training faces and finds the directions where faces differ the most from each other. Those directions are literally called eigenfaces. This They look like a ghostly blended face shape. We keep only the top n of them, reducing 10,000 numbers down to just 60 or 80. Finally, the support vector machine, SVM, takes a small set of numbers and draws a boundary to decide which of the 40 identities it belongs to. The best thing is there's no need of GPU. It takes under a second to process. Now let's look at the code. We let the code systematically test every combination. 7 values for PCA components and 4 values for C. That's 28 experiments, all evaluated with a 5-fold cross validation. So we are not just getting lucky. The answer was consistently somewhere around 60 to 80 components and C between 1 to 10, though it slightly varied depending on which seed we used. Pipeline B has 6 steps, as seen in the flowchart here. And the key difference from pipeline A is it starts right at step 2. Because ResNet 18 was trained on color images, we first convert each grayscale face to RGB and resize it to 224 by 224. Then it goes into the frozen ResNet 18 network. Frozen meaning we never change its weight, we just use it as is. ResNet 18 builds up its understanding layer by layer. Edges first, then the facial features, then identity. We tap into that just before the final output and take the 512 number summary it produces, normalizing it. It just means every face gets scaled to the same size, so comparison is fair. And those 512 numbers are then handed to Linear SVM, which classifies the identity in under a tenth of a second. As for the code for pipeline B, the key trick is removing the last layer of ResNet 18 that gives us the 512 number face description instead of a class prediction. We freeze all the weights so nothing gets retrained. The heavy lifting of extracting those embeddings only happens once. It takes about 43 seconds, and then we reuse them for every seed. Before trusting any results, you have to make sure the experiment is set up fairly. Both pipelines saw the exact same training and test images, no exception. Macro F1 means all 40 subjects carry equal weight, so a hard subject counts just as much as an easy one. And we never let the test set influence any decisions. Hyperparameters were chosen purely for training data. Okay, let's move on to the hyperparameter search results. Pipeline A swings from 93% to 97.5%, quite sensitive to the split. Pipeline B barely moves, sitting between 97.5% to 100%. The fact that it always picks C equals 1 is actually the most interesting result. It means ResNet 18's embedding do most of the work before the SVM even gets involved.
Okay, next we'll be talking about the metrics used and why. Firstly, we used accuracy since each identity has equal representation, making overall correctness a meaningful measure. Next, we use macro precision, recall, and F1 score. This macro averaging ensures that each identity contributes equally to the final score. So it is important in multi-class setting. Um, Moreover, we use confusion metrics and per class accuracy, which helps identify specific identities that are misclassified. And finally, we measured training and inference time as computational efficiency is critical for real-world deployment. Okay, next we will go on to the evaluation methodology. So to ensure a fair comparison, both pipelines were used the same identity, stratified split, 7 training images and 3 test images per subject. We evaluated performance across 5 different random seeds, which reduces the risk of a lucky split influencing the results. Hyperparameters were tuned using 5-fold cross validation also, ensuring systematic model selection. By evaluating across multiple seeds and reporting mean and standard deviation, we were able to assess not just performance but also robustness and stability. Okay, next we'll move on to our box and whisker plot over here to analyze our results. Okay, as you can see, our pipeline B shows a higher median accuracy and a smaller spread, which proves to have consistent performance. It also demonstrates that it's more robust and less sensitive to random splits. All right, next we will be talking about confusion matrix analysis. Okay, as you can see from pipeline A, it shows that a few off-diagonal errors over here, which means that some identities are confused. Pipeline B, however, shows almost perfect diagonal line, so fewer misclassifications. Okay, transfer learning embeddings produce more separable feature and representations. Next, we will go to our per class accuracy analysis. Pipeline B, which this orange line achieves near 100% accuracy for most identities, while pipeline A has some variabilities over here. So it indicates that pipeline B generally generalizes better across identities. Okay, next we will go to our runtime analysis. So our graphs here, we have the training time by seed and the inference time by seed. Pipeline B has a lower average training time and lower inference time per image. So it means that a faster inference makes pipeline B more scalable for deployment.
We have the result that is run on 5 or 6. Pipeline B outperformed pipeline A on every single metric. Accuracy improved from 96.33 to 98.5%. For F1 score, it follows the same. Pipeline A with 96.15, okay, for pipeline B 98.38. Pipeline B trains 20 times faster at 0.04 seconds compared to 0.87 seconds and runs 3 times faster at inference. Pipeline B is the clear winner, more accurate, more efficient. Pipeline B isn't just more accurate, it's also more consistent. Pipeline A standard deviation is 2.54% compared to pipeline B, which is 1.49%. A 41% in reduction of variance. 6, 256, and 789 expose pipeline A weakness. These 6 they subject with higher pulse and lightning variation in the test set, causing accuracy to drop. Pipeline B remains stable across all 6. Hence, in real-world deployment, consistency is just as important as peak accuracy. We drill into per subject accuracy. Pipeline A consistently fails on subject 36, 38, and 40. Subjects with noticeable pulse and lightning variation. PCA compresses faces into global pixel statistics, so any surface level change disrupt the projection. Pipeline B ResNet 18 features encodes higher level identity queues, making it far more robust. Both confusion matrices show strong diagonals, but Pipeline A has 4 to 5 misclassification versus Pipeline B, which only has 1 to 2, confirming that when Pipeline A fails, it fails more frequently.
Moving on to our next slide, I think it's important to take a critical look at our work. While our pipelines performed well here, we acknowledge some limitation when considering real-world deployment. Our biggest practical limitation is the tiny dataset. Since we are relying on just 400 images across 40 subjects, our results might not be suitable for larger, more diverse populations. Furthermore, our evaluation was strictly offline. We haven't validated how the system holds up under real-time webcam testing. To improve our system, we have few improvements. I would like to highlight 2 of them. First, upgrading our basic pre-processing to CLAHI for much better adaptive illumination handling. Second, replacing our generic ResNet 18 with face-specific model like FaceNet or ArcFace. If time permitted, adding data augmentation and ensembling our pipelines would serve as excellent secondary steps to maximize robustness. We can conclude our assignment with 3 points. First, pipeline B achieved a 2.17 percentage point higher accuracy than pipeline A, alongside 20 times faster training and 3 times faster inference. Second, our classical PCA baseline remains a highly viable, competitive, and interpretable starting point that requires 0 GPU. Finally, to push our accuracy towards 100%, the logical next step would be adopting face-specific model like FaceNet and implementing CLAHI pre-processing. Thank you for your time. We would now welcome any questions.